So for the recording, which is actually on this time, hello again, it's David, it's summer semester 2016. There's a lovely bunch of people here in the Polygon Lecture Theatre. I'm just going to quickly talk about orthogonal diagonalisation and orthonormal bases and that sort of thing. Ortho stuff. Okay. So all this is wrapped up with really trying to find a new set of coordinate axes for a subspace. So that's why we used it to do the conics. It may also be the reason the conics are there, so it felt like we used it for something. It's a bit tenuous because conics are more maths. But to a mathematician, using maths to make more maths is the only reason to have maths. So, and we're all antelope eat the grass and we're all connected in the great circle of life. So that's a really good thing to know about mathematicians, that maths is just used to make more maths. And so when they say, what do you use this for? And they give you the unsatisfying answer, well, you use it to make this other maths. You can think, do you know what? They don't know any better. I'll just let them have that one. Okay? So mathematics 1A or 1B is also mathematicians 1B, and what we've learned is mathematicians like to make more maths. So here we are, we're looking at orthogonal diagonalisation, and we've used it to talk about conics and quadrics, and that's what we've used it for. But in general, it's actually about trying to find new coordinate axes for things. So, let me see if I've got a good start. Right. Right, an orthonormal basis is a basis that is both orthogonal and normal. Okay, so a basis for, sorry, let me get my eraser. A basis V1 up to Vk for a subspace is orthonormal when Vi dot Vj is equal to 0 for any I not equal to j, and the length of Vi is equal to 1 for any I. That's the definition of orthonormal. You may also see it as Vi dot Vj is equal to 0 if I is not equal to j, and equal to 1 if I is equal to j. It's the same thing. Because, of course, the dot product of something with itself is the square of its length. So you may see it like this. I'll just put it there. Or Vi dot Vj equals 0 for I not equal to j, and 1 for I equal to j. You may see it written that way. In my head, it's this way, because this first bit says it's orthogonal. That's the ortho, and this says it's normal, everything's length 1. Alright. That's what an orthonormal basis is. The reason we care about orthonormal basis is that any basis is setting up a set of coordinate axes inside your subspace. And the thing is, that in an ordinary basis, the coordinate axes don't have to look at all like what you expect them to look like. The coordinate axes could be at skewed angles to each other, and they don't necessarily have to be marked out in the same scale. Okay, so you could have one that's marked out with the 1, 2, 3, 4 at distance 1, and the other one could be marked at distance pi on 3. Doesn't matter. Bases can be whatever way you want, but an orthonormal basis, well, that everything's at right angles, and all the marks along the axes are at 1 apart, as you would expect them to be. So here's a picture in my head. That's a picture. and once it's on the paper it won't be in my head anymore. You may have a random basis like this for R2, and what that would allow you to do is draw coordinate axes like this. And you can mark this one out in lengths of this big vector, and mark this one out in lengths of this vector, and this one can be marked out in lengths of this smaller vector. And then you can locate any point by saying how many of this vector and how many of this vector. So for example, this point here is 1 of V1 plus 1 of V2. Whereas say this point over here is minus 2 of V2 and plus 2 of V1, something like that, where the little one is V1 and the big one is V2. Okay, so every point in space can be found by doing combinations of these vectors, but what you have to do is is draw like dotted lines parallel to your axes, and you can figure out your grid points, but everything's all skew if they're all little parallelograms, and it's not pretty. And so therefore, what we would prefer is for our coordinate axes to be at right angles to each other for a start, and to be the same length as each other, and the two vectors marking out the same length on the two axes. So this is not orthonormal. Whereas something like this is orthonormal. I can remark my axes to be along a different length, not a different length, in different directions, but they're still at right angles to each other, and I just have a new set of grid lines which are sort of marked out, rotated from my original axes, but still marking out grid points the way I would expect them to. It's just rotated relative to what it was before. Right, so the whole point of orthonormal bases is that when I choose to write a vector as a linear combination of the vectors in the basis, then the numbers I use in my linear combination are precisely what they line up with on the axes. Whereas over here, if I line this up at right angles to the axis, it wouldn't come out to 1, it would come out to 3. So that's the picture of what we're trying to achieve, is a new set of coordinate axes. And the reason we might want a new set of coordinate axes rather than our original one is that the object that we are attempting to draw may be easy to tell what it is relative to the new axes. That's the whole point of conics. Okay, so I might have this random equation. If I draw it relative to the right new set of axes, I think that, oh, it's a circle, right, obvious. That's the idea behind it. Okay. Now that's the picture of why orthonormal bases are useful, but the other thing is that algebraically they're useful because of something that we used to want to do, well, you used to be asked to do in Maths 1A, is to write something as a linear combination of basis. So any vector in the subspace I am just being lazy.
Okay.
It's like writing a newspaper article. You don't put articles in the title. You know, you don't say the president. You just say president. Yeah. Just being lazy. Any vector in the subspace can be written as a linear combination of the basis. All right. So I know that any vector, let's call it W, is something times V1 plus something times V2 plus blah, 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 plus something times Vk. That's always possible. In fact, if it really is a basis, then there's exactly one way to do this. There's only one set of numbers that will go in these places. Alright, so that's true for any basis. Any basis, you can rewrite every vector in the subspace as a combination of the basis. For an orthonormal basis, it's even better because there is a particular thing you can do to calculate what those numbers are. When we're back in months 1A and they said, write this vector as a linear combination of these ones, you had to put them in columns in a matrix and row reduce them and all this stuff. No need to do any of that if it's an orthonormal basis. If it's an orthonormal basis, then the coefficient of VI is W dot VI. That is, W is W dot V1 times V1, and W dot V2 times V2, and W dot VK and VK. That is the magic, the algebra magic, as opposed to the picture magic, the algebra magic of an orthonormal basis. Okay, so for an orthonormal, for any basis, then it's possible to find what goes in these brackets, but for an orthonormal basis, you know exactly what goes in the brackets. It's the dot product of the vector that you're thinking of with the basis vector. Okay, so just as a specific example, just so that you know precisely what I'm talking about here. Let V be the span. Right, let V be the span of those two vectors, 1 on root 3, 1 on root 3, and minus 1 on root 3. And the other vector is 1 on root 2 minus 1 on root 2. That's a minus, by the way. It's not part of the fraction bar. 0. Right. Just give me a second. Oh. 2, 1, minus 3 as a linear combination of the basis. I mean, you would have to confirm that it really is in V, but this will tell you that anyway. Okay, so this is an orthonormal basis. The length of both of these vectors is 1, because without the root 3's, the length would be root 3, so divided by root 3. And without the root 2's, the length would be root 2. So they really are normal, and they're orthogonal because when I do the dot product of each of them, it comes out to be 0. So I'm going to say let V1 be 1 on root 3, 1 on root 3, minus 1 on root 3, and V2 be 1 on root 2, minus 1 on root 2, 0. Thank you. There we go, it's a bit better. One day I'm sure I'll go to total equivalence and all of my numbers will look like all of my other numbers.
Then you'll never be wrong.
Yeah, also never be right, but you know, that's the sacrifice we have to make. So these are orthonormal. The point is that this wouldn't normally be a straight exam question. Normally you would have found the orthonormal basis first, and then they would ask you to write something as a linear combination of them, so you'd know they're orthonormal already. These actually are orthonormal, and so I'm going to give this vector a name. W dot V1 is 2, 1, minus 3 dot 1 on root 3, 1 on root 3, minus 1 on root 3. What have we got? 2 plus 1 is 3. Plus 3 is 9. That's 9 on root 3, I'm pretty sure. No, it's 6. I was multiplying instead of adding. So 2 plus 1 minus 3 would be 6. And W dot V2 is 2, 1, minus 3, dot with 1 on root 2, minus 1 on root 2, 0. So 2 minus 1, which is 1 on root 2. And so therefore, so 2, 1, minus 3 is 6 on root 3, which I'm sure it would be better to actually figure out what that is, but I'm just going to leave it like that. Plus 1. Have I done something wrong here? No, it'll work. What's 6 divided by 3 is 2, isn't it? I think there should be a 4 at the front. Oh yes, sorry. That should be a 4. Which would make this a 4 plus 1 would be 5, plus 3 would be 8. And 4 minus 1 would be 3. Right. And now it is written as a linear combination of the vectors, and that is it. Like if you're asked to write something as a linear combination of other things, I've stopped now because I've written it as something times v1 and something times v2. I mean, if I really wanted to, I could have just put the v1 and the v2 in there. Just to check, which is what I was doing in my head, this should actually come out to 4, 1 minus 3. So we get 8/3. I'm just going to turn. Sorry. Okay. All right. I give up. That's a 5. Okay. So let me tell you something really important about what's happening here. If this does not come out to this, then it means that this isn't in the subspace. Yep.
If you've got a negative, then you 1 over root 2. 1 over root 1.
Yeah?
Down.
Still not going to work though. Right. So here's a useful lesson to know, is that if this, when you figure it out, does not come out to this answer, it means that this wasn't in the subspace to begin with. The only way that this vector can be equal to what you get when you do this process is if it was in the subspace. So if they had asked instead, is this vector in that subspace? All I would need to do was figure out what it would be as a linear combination and see if it's the same answer. So I could change the question, but I'm pretty sure it's a 5. That 4. I'm so sorry. If I was your lecturer, you would give me bad cells for organisation. And by rights, you should have. So let's try it one more time. It's still not going to work. I just give up. I really tried. It really should work. 3 minus 3. Have I done something wrong in my calculation? Oh, that's because these numbers should be changed now, shouldn't they? All right, so if that's a 5, 5 plus 1 would be 6, minus 3 would be 3. Oh, look at that, everything's going to work now. Yeah. Sorry? Oh, yeah. That's okay. It's 9 then. So 5. Right. And good, because 9 on root 3, and if I multiply it out by all those root 3's on the bottom, I'll get 9 on 3. 1 minus 1 plus 4 on 2, 1 minus 1, 0, which is 3, 3 minus 3 plus 2 minus 2, 0, which is very much 5, 1 minus 3. And the world makes sense again. Okay. Right. Sorry about that. Okay. So as a check, it should work. And if it didn't work, it wouldn't have been in the subspace. So they could just as easily ask you, is this vector in this subspace? You would do this process and see if it came out to the same answer, and if it didn't, you would go, not in the subspace. So, for example, just to be sure I've gotten that, e.g. is 4, 1 minus 3. Is it in the subspace?
Yeah.
Yep.
Isn't that also the orthonormal projection as well?
It is indeed the orthogonal projection, so that's just about to say. Okay, so I can do this process on any vector, whether it's in the subspace or not. And the question is, what is it? The answer when it's not in the subspace is different to the original vector. And what is it? It's the orthogonal projection onto the subspace. Okay, so I'm getting ahead of myself, but I will say it afterwards. But while I'm at it, I'm just going to say this. So I could do the projection of 4, 1 minus 3 onto the subspace. And to do that, I would do my vector dot with each of the other vectors. Which before came out to 8, I believe. I've got 4 plus 1 is 1. So the projection is 8 on root 3 times 1 on root 3, 1 on root 3 minus 1 on root 3 plus 3 on root 2, 1 on root, which is 8 thirds of 1, 1, 1 and 3 halves of 1 minus 1, 0. Let's see, 8 thirds plus 3 halves would be, oh my goodness, 16, 6 plus 9, 6, and 16, 6 minus 9, 6. Okay, so that's the projection. And it's not equal to the original vector. Not in the subspace. All right. So, cool. So sorry for those listening and basically all of you for not doing this earlier. But the idea is that calculation can be done on any vector. And if the answer comes out to the same as, if you have a vector you know already is in the subspace, you're just going to get the vector that you had again, but written in a different way. Because you're writing as a linear combination of the original, of the basis vectors. But if your vector wasn't already in the subspace, you're going to create a vector that is in the subspace. Because you've done it as you've written what we've written here, this is a combination of the basis. So it's a vector that is in the subspace. So since the original vector wasn't in the subspace, and this new vector is in the subspace, they can't be equal. But what this is called is the orthogonal projection. So that's what it is. So here's the idea. So if you have, orthogonal projection. So the orthogonal projection is that if you have a subspace V with basis V1 up to Vk, and V1 up to Vk are an orthonormal basis, that's important, then the projection of W onto the subspace V is, well, you know the projection is a new vector that's in V, so you know it's something times V1, I will put something in these brackets, plus something times V2, plus something times Vk, and the something that it is the dot product. It's exactly the same calculation you would do if it was in the subspace, you're just doing it with a vector that isn't in the subspace. And there you go. And that's the orthogonal projection of W onto V. So just note, 3 notes. 1, it has to be an orthonormal basis for this to work. Okay, it has to be an orthonormal basis for this to work. So if you look at it and it's not an orthonormal basis, you cannot do this until you turn it into an orthonormal basis. Number 2, if the vector is already in V, then the projection is just equal to W again. So the projection doesn't do anything if you're already in V. And 3, if W is not in V, then the projection is not the same as what you had before. Whoops, sorry. There's 3 important things to note about how the orthogonal projection works. So that means if you've gone to all the effort of finding an orthonormal basis, if someone asks you, is this vector in the subspace, just figure out what its projection is and then you'll know. Because it's the same as what you started with, it is in the subspace, and if it's not the same as what you started, then it's not in the subspace. It only works if you've got an orthonormal basis. Which begs the question, how do you find an orthonormal basis? And when I was in first year, we used to call it the Gramm-Schmidt process. Sorry?
You read that in the exam?
No.
That's a typo.
No. So presumably, mathematicians Gramm and Schmidt invented this process, and this process does not just tell you how to find an orthonormal basis, but for a mathematician it's really important because it proves that such a thing as an orthonormal basis actually exists.
Can you put the last thing up just up the top?
The 3 notes.
So the Gram-Schmidt process, the reason why it has a name is it's not just because it helps you find an orthonormal basis, but because it proves that the orthonormal basis is such a thing that actually exists. And mathematicians really don't like to talk about things that don't actually exist. Well, in the mathematical sense, because the number I really does exist because it's because
Electrical stuff.
well, no, that's electrical stuff. You're talking mathematicians here. The complex numbers really exist because they are the quotient field of the polynomials So that's why a mathematician knows that the complex numbers really exist. So to a mathematician, you need a mathematical reason why something exists. Okay. So there has to be. How do you find one? And you find one using the Gramm-Schmidt process. Now we know that everything does have a basis of some sort, and the Gramm-Schmidt process is a way of turning an ordinary basis into an orthonormal basis. I think that's how you spell Schmidt, isn't it?
You added too much C, M, and I, and D.
Is it just M? Is it just SMIT?
Yeah, S, H, I,
No, it's not. He's telling you right shit.
See, now I need to look it up in the notes.
He just wanted you to write shit. So he told you.
I am not that immature. Yeah, that's what I wanted you to do.
Oh. That would have been really funny.
I know, why did you do that?
if I understood what you were doing. Okay.
Or you didn't, but you took away from them as well.
Yeah. So the Gramm-Schmidt process turns an ordinary basis into an orthonormal basis. And the way it works, so you may not have noticed this, the way it works is that you progressively replace each of your basis vectors by a new vector. Okay, so really what you're doing when you do the Gramm-Schmidt process is doing a list of different bases. You have your original basis, then you have another basis which has one vector change, and another basis which has two vectors change, and another basis which has three vectors change, and you're progressively changing your basis one vector at a time. Yes?
How do we get the basis in the first place?
By the processes that you found bases in Maths 1A. So, ways to find bases, I will talk about shortly. Okay. So, well, all right. Step 0, have a basis. Okay. So, just so you know, there are several ways to find bases. Way number 1 is to happen to think of something that works. Yes. So just some examples of finding bases. Something like that. You're allowed to say something along these lines. It's a plane. It's a plane in R3, so it's two-dimensional. So it has two basis vectors. And if you happen to think of two vectors in it that are linearly independent, they will be a basis. You're allowed to do this kind of working if you want. So you could say, well, let's call it V. 1, 1, 0 is in V because 1 minus 1 plus 0 is 0. And 1, 0 minus 1 is in V, since 1 minus 0 minus 1 is 0. And so therefore they are a basis because they're independent and there's two of them. Because it's a plane and it only needs two. So two independent vectors in V are a basis for V. So therefore basis is 1, 1, 0, 1, 0 minus 1. That is a perfectly reasonable way of coming up with a basis. It's probably a more straightforward way, but if you happen to think of a basis, then that is a perfectly reasonable way to make a basis. The other way to make a basis is to solve the linear equation. So, or solve the equation. There are multiple ways to solve the equation. You could, if you wanted, put it in a matrix and stick in three variables. That would probably be more useful for two equations. If you had two equations, you could put them in a matrix and do the three variables. With one equation, it's probably quicker just to say, oh well, x equals y minus z, which means that x, y, z is... Well, we just said that x was equal to y minus z, but we don't know what y and z are, so we'll just leave them as they are. And we have y lots of 1, 1, 0, because I picked out all the y's from this, and z lots of minus 1, 0, 1. And so they are our basis, because everything in my subspace has been written as a linear combination of those two things. Yay! Therefore basis. You'll notice that it's slightly different to the previous basis I had. It's just that this one is minus this one, but that's okay. Doesn't matter. So there are two alternative ways of finding a basis for a plane. Alright, if you're in 3 or 5 or 7D or something, you could the best things to probably rewrite is to put all your equations in and solve them using a matrix and chuck in your free variables. That's the quickest way to find a basis. Okay, so the next step is the whole process. And the process proceeds one vector at a time, and each vector you do 3 things to, except the first vector, which you only do 1 thing to. So, and it goes like this. So some people who've been in the Maths Learning Centre know this already, but I'm going to do it now. It is to the tune of Fairyland Clickety Clock from the television show The Fairies. It goes, we use the Gram-Schmidt process because we need to find an orthonormal basis, and to start we normalize, project, subtract, normalize, project, subtract, normalize, project, subtract, normalize time. Thank you. And it's easier to do it with an example.
How is a 6-year-old supposed to do that? Just start talking about university maths and you get 5.
I've always wanted to be the person on Play School who makes all their stuff out of cardboard.
Yeah, they did that like a couple of months ago and they accidentally made a bomb.
Did they?
Yeah.
Accidentally. Right. What's the parents know?
Did they write it?
There we go. Nice 3-dimensional vector space in R4. I should point out there's absolutely no reason why we can't have numbers other than whole numbers in these things. I mean, we could have just as easily had like a half or 3/5 or 2.8761 or √7. There's no reason why we have to use whole numbers. It's just that, just like everybody else, whole numbers feel nicer to people who write your exam. So, just pointing it out. Okay. So, here we have, we want an orthonormal basis for this subspace. And we will do what the song says, we will normalise, and then for the other 2 vectors we will project, subtract, normalise, and project, subtract, normalise. So, I will give them all names. Do you call them, what do you call them when you start? There's no particular reason why you have to give them particular names. When I learned this for the first time, the original vectors were V and the final vectors were U. Okay. Because the final vector were U because they were unit vectors, but you know, that made sense to me at the time. So these are my original vectors. I'm going to change them one at a time. So I will normalise. So to normalise U1, I'm going to need to find its length. Do we use double lines for length in Maths 1B? So what is it? So the square root of 1 squared plus 2 squared plus 1 squared, which is √6. And so V1 will be 1 on √6. My recommendation number 1 for doing this in practice is not to multiply it into the vector and just leave it out the front. While if you were doing Maple TA, you would have to multiply it into the vector, but this is not Maple TA, this is handwriting, and this is better for handwriting. Alright, so now I have replaced my first unit vector with a new, my first vector with a new unit vector, and then I have a new basis which is V1 and U2 and U3. Now I'm going to deal with the second vector. So there are 3 steps. Project. So the projection of U2 onto V1. That's what we're doing. We are projecting the vector, the next vector that we want to fix onto the vector that we've already made. Oh, frill. I just need a bit of space before that. When I do the projection of U2 onto V1, I'm going to need to do U2.V1 because that's how you do projections. You do the dot product and then you multiply by the vector. So I'm going to need to figure that out first. I should have left myself a bit of space. U2.V1. One of the morals of these tales is in exams, leave space between things so you can fill in things that you forgot. And so what have we got? 3 times 1 is 3, 0 times 2 is 0, 2 times 0 is 0, 1 times minus 1 is minus 1, so 3 minus 1 is 2. So that's what we have. So the projection of U2 onto V1 is 2 on root 6 times V1. Sweet. I suppose I could do a third. That would be nice. Okay. Now you may think that I've got 3 steps for each of these and the lecturer only had 2, but that's because I've split the lecturer's steps into one of the lecturer steps into 2 pieces because I find it hard to do it all in one go. So I project and now I subtract. So my V2 dash is my old U2 minus the projection of U2 onto V1. So I have my old U2, which was 3, 0, 2, 1. Take off 1/3 of 1, 2, 0, minus 1. Which is, so 3 minus 1/3 would be 2 2/3, which would be 8/3. Or I suppose if you like, 3 is 9/3, 9/3 minus 1/3 is 8/3. 0 minus 2/3, 2 minus 0/3 is still 2. 1 minus minus 1/3 would be 4/3. Now here is piece of advice number 2. My first piece of advice was to avoid multiplying in your root 6 because it's just going to get multiplied by another root 6 later. My second piece of advice is not to use this vector at the next step because V2 dash is just the direction that V2 points in. I don't care what V2 dash is, I just care what direction it points in. So I can multiply or divide this vector by whatever I want and use the answer instead. So I'm going to multiply this vector by 3. I will use a triple equality sign, which means equivalent to as opposed to equal to. And I will multiply everything by 3 and get 8 minus 2, 6, 4. And even better, I could divide everything by 2 while I'm at it. And that's where I am. I'm going to use that vector because it's better.
Someone told me that triple thing was this is defined to be this.
Nope.
Okay, so it's equivalent.
Equivalent. So with triangles it means congruent.
Yeah.
It has multiple meanings, but it's there to say this is just as good as. Defined to be is a colon and an equals. Okay. So now the last step is to normalize. I've done the project. where I multiplied it by the did the dot product and multiplied it by the dot product, and then I've done the subtract, and then I've made sure I've cleared all my fractions so things are easier. Now I'm going to normalise. So the length of V2 dash is the square root of 16 plus 1 plus 9 plus 4. What, root 30? Awesome. And so therefore my new V2 is 1 on root 30 times 4 minus 1, 3, 2. Okay, just to keep my reader focused, I'm going to highlight the vectors that I have created. So I've now changed 2 out of my 3 vectors. My first vector I will have to do again, and so I will do project, subtract, normalise. So project. But the project stage gets harder each time. Well, not harder, but longer. It's just as easy, it just takes longer. So I have to project U3, which is here, onto the 2 vectors that I already have made. So let's figure out the dot products. U3 dot V1 will be 4, 2, 2, 3 dot. And U1 was, V1 was 1 on root 6. 1, 2, 0, minus 1. 4 plus 2 is 8. Minus 3 is 5. Okay, I think that's right. 4 plus 2 plus 0. Crap, 4 plus 2 is 6. No, it's 4 plus 4. 4 plus 2 times 2 is 4 plus 4, which is 8. Minus 3 is 5. Yeah, okay, good. So don't give a revision seminar before you do your exam because you'll be really tired. Sound advice. Good thing I'm not doing your exam. So I have toyed with the idea before, but really, certainly. U3.V2, I'm using the V2 that I just made, just there. So let's see, 16 minus 2 minus 6 minus 6. 16 minus 6 would be 10. 10 minus 8 would be 2. Okay, so I've done my dot products. And so now my projection is... So my V, no, it's just the projection. Are we okay?
Is this supposed to be minus 2 plus 6 plus 6?
Oh yes, of course it is. That's going to totally make it different, isn't it? 16 plus that would be 26. Because 6 plus 6 is 12 minus 2 is 10. Yep. Thank you. Wouldn't it be nice if you had a team of people checking your work for you in the exam? I've just brought my entourage with me. Oh crap, missed the 1 on 30. Oh. Alright. Alright, this is when I start to really hate fractions. But that's okay. So my way of dealing with all of this stuff is to so 26 on 30 would be 13 on 15, wouldn't it? It's not really much better. And I really would normally cop out and get a calculator to do half of this for me. But well, I know what 4/13 is, it's 52. And then I will add all those fractions together and it will come to whatever the answer is. So yeah, this is where I get someone to help me. 5, 6 would need to be times by, it would be 25 on 30 plus 104 on 30, so 129. And that's actually the same as 5/3, isn't it? So 15 minus 13 would be 2. And we've got 25 on 30 plus 52. 25 plus 52 would be 77.
Is that 120 something?
That's 129. Which is equivalent to 129 to 39.77, which I have not the slightest hope of factor of dividing anything out of. And so I will just have to normalize now. Oh crap, I have to use this as it is. I haven't done that bit yet. That was the project.
Is that 34 and 15?
I think it's a 39. Have I done that wrong? Yeah, 39. That was the project. I have to subtract yet. So my V3 dash is my original U3, which was 4, 2, 2, 3, and I have to take off this. Yep.
Projections take, you have to take the two, you added them there.
Mm.
Yeah, I think you added them like more.
No, I do the subtract in a separate step.
Okay. Yeah.
Because otherwise I lose all my minuses. So that's one of the reasons I do it this way, because otherwise I get more minuses, like double minuses, and I just lose them. So instead of doing thing minus this, I do those two bits, and then I take them off the other thing. So in your book it's thing minus this, right? Well, I do that plus that, and then I get an answer, and I go this minus the answer. Because otherwise A, it fits into the song better, and B, I don't lose minuses quite so easily. So let's see, 4 lots of 30 would be 120.
I think you've done the addition slightly wrong.
Have I?
Yeah, I just put it in the calculator.
Alright, what's the real answer?
43 over 10, 4 over 5.
What's that?
The first one's right.
It's the one to be under.
It's a second value is 4 over 5.
Oh, is it? Oh well. So So, this from this stage to this stage?
Yeah.
Yeah, I'm sure I did that wrong. If I was actually being good to myself, I would actually try and figure out my fractions not in my head. So the 5 6 plus 52 15ths
Is 43 over 10. You had that one right.
Okay, they cancel, do they?
Yeah.
Oh, look at that. Who'd
The
have
next one is 4 over 5. 13 over 5.
Yep, that makes sense.
And 9 over 10.
Well, that's much simpler. Only reason to have calculators in an exam, to check your fractions. 9 over 10. Look, I'll copy it here and then you'll know. Well, that's better.
Yeah, that's what I was trying to
Thank you. So 40 minus 43 would be minus 3 on 10. Two minus 4/5 would be 10/5, so 6/5. So I think that's right. And then that's equivalent to minus 3, 12 minus 6, 21. And I could divide that by 3, I suppose. Like that. So what I did is I times this one by 10. Right. And so therefore now we normalise. One day I'll look like a boss and do this without making a mistake. Or alternatively choose my numbers to begin with in my question so that everything looks like it's easy. But perhaps that's not the best plan. The length of V3 dash is the square root of 1 plus 16 plus 4 plus 49. 49 plus 1 is 50. 16 plus 4 is 70. It is 20, so we've got root 70. And so therefore V3 is 1 on root 70. At this stage, what you're supposed to do is check to see if they really are orthogonal with each other. I'm terrified that my answers are wrong. But you're supposed to go, all right, well, just a second, just to check. My V1 and my V2, 4. Minus 2 is 0. Yay. My V1 and my V3, minus 1 plus 8 would be 7. Minus 7 is 0. Okay. And my V2 and my V3, you just ignore the number out the front. Minus 4 plus 4. Oh, sorry, yeah, minus 4, minus another 6. So what are we at now? Minus 14. Plus 14 is 0. Yes, they're all orthogonal to each other.
It's a little bit disconcerting that you're cheering about doing something which is supposed to be really easy.
I never said it was easy.
It's supposed to be because we use it to do all this other crap.
All right. Now, 2 important points to make about the Gram-Schmidt process. And they are, in an exam, you almost never have to do 3 vectors.
That's good.
Well, it hasn't happened yet in my 7 years of experience in the Maths Learning Centre. So
if it does happen, can we come to you?
you can come to me and say, gee, David, you said almost never. You were right. So the reason is that usually you use the Gramm-Schmidt process because you're finding an orthogonal diagonalization matrix. And therefore you only need to do the Gramm-Schmidt process within each eigenspace separately. And almost always, and let's think about it, you don't know what quadrics look like in 4 dimensions, so you won't get 4-dimensional quadrics, because really, what reason do you have to orthogonalize a matrix, orthogonally diagonalize a matrix, but to find out what a quadric is? And you don't know what the 4D quadrics look like. And so you have 3D quadrics, and the only way for a 3D quadric to have an eigenspace that is 3-dimensional is it to just be something x squared plus something y squared plus something z squared to begin with. And you know what that looks like already. It's an ellipsoid. So there's no reason to do it then. So that is why you will never see it in an exam. Almost never. Okay. However, there's also sometimes they may ask you to orthogonally diagonal, they may ask you to Gramm-Schmidt something, but there'll be a heap of zeros in it. And so they might already be orthogonal, half of them might already be orthogonal to the others already. And so your process will be cut down because there'll be a lot of zeros in your working and it won't be quite as complex as the one that we had there. Okay. So that was orthogonal projection. And that was the Gram-Schmidt process. And I gave him a little song, which I actually asked the writer, the writer of the fairies for permission to use, by the way. And she said yes. After she said, "What kind of psycho are you?"
Had she done this math before?
No.
So she's got
Her email was, I was going to dismiss you as some sort of crackpot, and then I thought, maybe you're serious. So yes, I do have permission. Not that that's stopped me before, for singing things in lectures. And the last thing, I suppose, is stuff about quadrics, which I could talk about if you wanted, but I have satisfied Danny in talking about orthogonal projection and Gram-Schmidt process. So I might stop there and just take a couple of requests for the last 20 minutes.